I think you might be able to.
Hmm.
All right, we're now live, and hopefully a few more people will join us soon. So I think we might as well just get right into it. The items on the agenda were to first go through the outstanding pull requests. So if everyone can go take a look at, let's first look at the ones that are looking at just the Enzo Dev pull requests.
Cool.
The only two that are on there are one from Philip Greet, who I haven't met, and one from Dave. Dave, let's start with yours. This zero acceleration thing. What's happening?
Nothing's happening with that right now. It's a super minor fix. My first iteration of it is clunky, so it was requested that I make it a little more streamlined. My first version of streamlining failed, and then that's as far as I had gotten.
Okay.
So it's a reasonably minor adjustment to a kind of rare corner case when you're using an accreting particle point source or a point source gravity and no other gravity source. If you're not using self gravity, you're just using like a point source gravity or a background potential. Then the gravitational acceleration just accumulates on itself.
Okay.
So that's the problem. The fix is just have a loop that zeroes it. I tried to do it in a slick way, and that failed. I tried to do it in a clunky way, and that's functional but clunky. So it's an afternoon of coding, but such an afternoon has not presented itself yet. So I can prioritize that if that's something that people care about.
Or if it's completely up to you.
All right.
We can leave a comment on there and just say what needs to be done.
Okay. I think
if someone gets anxious, they can go for it.
Right. I think that's fine. It's on my to-do list, but it's grant proposal season and
sure
all that fun stuff. So.
Is this 117? Hi, Brian.
Yeah, that's 117.
Yeah.
It looks to me like, it's 3 lines, right? 4
yeah,
lines?
it's 3 lines of code. I just need to make sure that it's tested. So.
I see.
I actually, this actually, Yuan Lee and I went this problem, and I think this would work. It's just that you need to include this within the dim. So there's a dim there, which is not defined because it's not inside the.
What are you looking at?
Oh yeah, totally. The if self-gravity equals 0, dim isn't defined inside that if statement.
That's true.
Okay. Oh.
So actually, Dave, you want to change that just to fix it in the most natural way, and it works.
Oh, okay, sweet.
Yeah, we just figured that out. So
Okay,
I think you can correct it and resubmit it, and it'll work.
Okay, cool. So which I haven't looked at this code in a little bit. What exactly did you just put this? You just put the if self-gravity inside of that dim loop before?
Yeah, I think that's right. I'll get Yuan to send you the code that she used.
Yeah, that'd be fine. I can update that. Yeah, cool. Hey, sweet.
Okay. So there's this PR 173, and this is Philip Greet changing the header include order and fixing a missing counter and write parameter file. It seemed like this was good for a while, but then he updated it with a bunch of changes for the include file. So Nathan, do you want to comment on this?
Sure. So it's not totally clear to me why this was necessary. I think he had to compile with some non-new compiler. It failed. Sometimes that happens. Like I've had experiences where includes are fine under GNU, and then under like Intel or something, I have to change the include order or something. So he did that for 2 files, and it was a totally inconsequential change. So I thought it was okay. And then he went back and decided that he wanted to change all of the includes for every single file in Enzo, which I thought was a little extreme. So I unapproved it, and now we're talking about it. For what it's worth, in Enzo 3.0, that's the way it's been for a long time. The only issue is that if we put a lot of stuff in pre-includes.h, like we have in Enzo 3.0 right now, that significantly increases the build times because we're basically putting all of the STL headers into every single file. It makes it easier to develop certainly if everything's in pre-includes, but it totally changes the way includes have been worked in Enzo 2.x for a couple of years now. So I don't know what the best course of action is.
Well, and if we make incompatible changes between 3 and 2 in a particular way that touches every single file, then that's going to be much more difficult to merge if such a merge ever happens.
Yeah. So I think we should just leave a comment for. Well, do we want to just fix the piece that he fixed for the right parameter file and submit that as a different pull request? I'm not sure how fast we'll get a turnaround from him.
Did that already happen? It looks like that's in the multi-refine region stuff.
Oh, okay, great.
I don't know because it's still it's not showing up. There's no diff, so we can't even look at it. Let me look in the source.
Okay, I'll put that on my to-do list to make sure that fix is in there. And then we can move on from there. Does that sound okay?
Yep.
Yeah. Great. All right, let's get some Enzo 3.0 action going here. Or rather, the Enzo 3.0 repository. So, which one do we want to tackle here first, the merge or the field objects? Nathan, let's start with the merge with the active particles.
Sure. So, yeah, the active particles work. We've run them with like simple cosmology problems, and while the answers aren't identical to 2.x, they're statistically the same. The halos end up moving a little bit with respect to each other, which I think is just due to chaos in the gravity solution. I tried to get bitwise identical results, but it ends up being impossible because before the star particles and the dark matter particles were stored in the same particle arrays, and they were sort of mixed up, while now the active particles, so the star particles, and the dark matter particles are in 2 different arrays, so they can never be summed in the same order, which introduces machine precision level round-off errors, which then diverge in the end. But the results, as far as I can tell, look fine with a cosmology simulation. Yeah, I've been using the accreting particle stuff for months, and that's totally fine. So, yeah, that merge is basically all of the development in Enzo 2.x for about 6 months, and then also sync particles, or sorry, not sync particles, also active particles, and yeah, that's basically all of the development in Enzo 2.x until just before MHDCT was merged in. But Matt wanted to wait a little while to improve that code base before we brought it into Enzo 3.0. Yeah, so I personally think it's great to go in, but it's up to everybody else.
Oh, sorry, I was just talking to the mute. If it works and passes all the tests, I don't see any reason why it shouldn't go in.
So I think the only concern would be whether or not this will work for many tens of thousands of star particles. But I think we won't know that until it's merged in and somebody tries it. So I'd also be inclined to just go for it, merge it in. Is anybody worried about the non-bitwise identicality?
No, I think
it's within the bounds of what we've seen even within Enzo 2.
Okay.
Just do the same scenario twice in parallel, and you'll get the same difference.
Yeah. Okay.
Though, since the active particles do have to interact with multiple grids, it might get ugly with lots of grids and lots of particles, right? So.
Yes. So the way the star particles work right now with active particles is they don't interact with multiple grids. They do the feedback using exactly the same methods as in the star makers.
Oh, wonderful.
So you only get the multi-grid feedback if you explicitly add that to your star particle. So like right now, Sen-Ostraker star particles are identical to the old Fortran Sen-Ostraker particles.
Sweet. Okay. So in other words, if you want to use many active particles to do something interacting with lots of grids, then whatever computational cost is just something you're going to have to bear.
Yep, and we'll probably have to do something algorithmically different than the way it's handled right now. Right now, it's optimized for small number of particles, like of order less than 1,000. So if you want to do fancy feedback with millions of particles, you're going to have to do a bit more work. But that's still difficult in Enzo 2, so...
Yeah, it is. Okay. Seems fair to include it to me, then.
So does that mean all types of star particles are working correctly?
Only done testing with Sen-Ostraker, which I think covers most use cases. There are star particles for Kraftsov and the Gadget star particles, but they haven't been tested.
Okay.
Well, I'm not even sure the Gadget star particles work, because does Enzo 3 have the Gadget cooling in it?
I think so.
Oh, okay.
Okay, so I'd kind of be in favor of just clicking the merge button here. Is anybody opposed to that just happening?
No, do it.
Yep.
Do it.
Yay!
Congratulations.
I'm going to let Bitbucket work on that for the next half hour. But that's in the pipe. All right, congrats, Nathan. And Matt,
thanks everybody else who worked
if
on that.
John was here, he would get some credit too. All right. Yeah, that's still going. So, Matt, do you want to talk about field objects?
What should we say? I guess field, yeah. I mean, they work in the cases that we've put them in there, and there are a bunch of tests. I'm totally down for including them, but I think that until they get threaded throughout the code or people start using them, then their utility will be somewhat limited. That being said, I think that they provide a lot of utility, and Greg and I have started looking at how to extend them to other regions like copy overlapping zones.
Can you give us like a brief overview of
Yeah.
Sure. Basically, you've all used NumPy, right?
Yeah.
Okay, so field objects are basically NumPy arrays with a limited subset of things that they handle, but they also handle overlaps. So let's say you've got two grids and they overlap a little bit. If you add one to the other, then what ends up happening is only the region that they overlap gets added. So they're basically NumPy arrays with, with all the operator overloading and so on that comes from that also manage overlap regions and that can handle edge, face, and vertex and cell-centered data. So they'll figure out, what you do is you describe the number of active cells that are contained by it, their left edge, and the centering of the data, and it will manage all of the sizes of the arrays and the allocation and the deallocation, as well as naming them by fields, managing their interpolation, so how they're conserved and so on, and the overlap.
Right, so for instance, you could say, at this point you can say this field object of density times field object of temperature, and it would do that multiplication kind of in one single line. There wouldn't be a loop over IJK indices, and it would only do the loops internally over the edges, the cells or vertices or edges that overlap with each other, right?
That's right. They also have information about the mechanism by which they should be interpolated. And so, for instance, if they need to be multiplied by density, you can call, interpolate or whatever, and it manages multiplying by density, interpolating, and then dividing by density.
Yeah. So the interpolation part of the code is the primary spot where they've been implemented as being used in the actual code base, right?
That's right. And it's also the biggest pain point for adding new fields, because what this will do is it will get rid of that should be interpolated or whatever the ifdef is in typedefs.h that just does field number comparison. Cool. And instead each field is now a first-class object that has information about how it should be interpolated. That's cool. There's a registry of fields as well. If you look at fieldregistry.c, it actually sets up density, total energy, gas energy, all the fields actually that are in the code itself. And you can pull up fields by accessing the grid object and then using a string to identify the field. So instead of having to search for dens number, you would just ask for string density.
And is it literally grid of density, or is it something else?
No, it's not grid of density because I didn't want to overload that. It's like grid. It's like field objects and then the string. But pushing it into the grid would be okay too. And right now they sit on top of the grid, and so this could go in and it shouldn't cause problems with existing code, and we can piecemeal replace it because the field registry that's affiliated with the grid doesn't actually have each field object can either have a pointer to data or a pointer to a pointer of data. And so it sits on top of the baryon fields array, which is an array of pointers, and it doesn't try to manage any of that data itself. However, you can also have it manage the data itself. So when one of the field objects gets destroyed, then it destroys the underlying data that it's allocated.
So because of that, we can kind of piece by piece replace the existing machinery with the field object machinery. So it can kind of be implemented in place without a significant amount of pain.
That's right. And you can see where that's done in grid interpolate field values.
Right.
Where I've left in the old commented stuff. And then, like for instance, the diff for lines 388 through 413.
Mm-hmm.
I've left commented the old field type as density call, and then where it manually calls the Fortran routine to do div 3D, and I've replaced it with a way of doing that with field objects. Although something that Tom pointed out when we chatted on a couple days ago was that this uses the divide method, but I've also overloaded all of the operators, and so this could just be iter second divided by equals fd dens.
Cool. Yeah, I think this is the kind of necessary path forward for Enzo development. I think the field object stuff really takes care of a lot of the old baggage that is just difficult to maintain and difficult to scale. I think it really solves a lot of problems. A lot of problems that I had when I was developing the MHD stuff. It takes care of that. It's going to make a lot of that less ugly. I think it's a good path forward.
Thank you.
Yeah. So does it so kind of for your development trajectory, do you just need to have this pull request accepted, and then we start banging on it and kind of merging pieces in as they work? I mean,
yeah. So Greg and I had a list of places that this would be really nice to implement and utilize, and I think doing that would be the next step. Yeah.
So what are those?
Those copy overlapping zones, deposit mass fields, You could do the equation of state calculations with the field objects, for instance.
Those would be pretty cool.
Stuff like copy overlapping zones is ripe for that. I mean, it would decrease the code count.
Yeah.
It would shrink it by 90% or something like that, and just make it so much more readable.
Yeah.
Because one of the things we did was each grid also has a spatial, or each field object has a spatial extent which is disconnected from the grid spatial extent. So you should be able to do, things like that with it.
Great.
So there's also cool things that we could do once it's in there, because now you have all these loops that are basically internalized in Enzo, and now instead of editing every loop in Enzo, you could edit one loop and, for example, see if you could thread over that loop. This is something I'd really like to see happen, because if you could just thread over size, you could get some awesome OpenMP speed up on this.
So you could just thread all of your multiplies in one step.
Yeah.
That's awesome.
That's really cool.
Cool.
Very nice. So what did you say that the best example of this implementation is again? I want to write it down.
Interpolate field values is a good one.
Like field values. Okay, great.
I had a question about the collapse test that's in your branch. There's a thing. No, I can't remember what it's called. There was a function that remap something.
Reconstruct field mapping, and so what that does is it just reconstructs the field's object, and in fact, I don't think it needs to be called.
Okay.
But what it does is so you've got the fields handle that hangs off the grid object, and that acts like it's an STD : map, and that. So what reconstruct field mapping does is it goes through. Let's see if we can pull up that. If I can pull up that code. Where is it? Well, anyway, what it does is it goes and it compares the numbers against the strings. That's all. It's basically it has to happen one time.
Yeah, so it's the kind of thing you can stick right before or right after all the initialization happens. It gets called every time the code runs, and then you just have that built kind of automatically.
That's right, and in fact, grid inherit properties calls that.
Okay, I was looking for the source for that. Where does the source for reconstruct field mapping sit?
I actually can't find it, and I know that the stuff that came off that compiled because Sam compiled it. So let me.
Okay. I couldn't. I was looking around for it the other day, and I didn't see where it actually happened. But I think.
I think it actually needs to be added. So let me.
Okay.
By the way, I'm going to take a look at Dan's questions. If you don't have the group chat open, he's got a few in there for once we get through this part.
And my connection isn't all that good, so I figured I'd just email.
Yeah.
Yes, it can. We haven't implemented the logical not operator, but that's been on our path for that. So right now, the idea is that you would construct face regions, and that would work. For the second question, would this work one field at a time? Yes.
Great.
And could this work for the potential field that is currently larger than an Enzo grid? Also, yes. I'm going to update my pull request real quick with this
Cool.
field that I forgot, or this file that I forgot.
So Matt, you were originally treating it as a separate library. Are you still doing that, or is it just being bundled with Enzo?
Right now, it's being bundled with Enzo. I had no. The idea wasn't to keep it as a separate library for very long. Unless you think that it should be. I don't know. The problem with that was always that keeping it as a separate library meant having to jump through some hoops in order to get the float double int long pound ups in there.
Yeah. No, I was just curious. It's fine the way it is.
You can always pull it out later if you want to develop it for some more general use.
Just as a quick question, are we actually planning to get rid of that float double?
Yeah. I
Sounds
think
like Jeff
in
just
Enzo 3?
volunteered.
Yeah, Jeff, you volunteered for find replace.
I think we all want to. It's just super hard.
Yeah. So I've actually let's finish the field objects thing real quick. So I think basically once Matt updates the pull request with that missing file, are people good to go?
Sure. Yeah.
I mean, it doesn't break anything, and it significantly makes things better. So
Yeah.
Let's do it.
Okay, cool. So we'll wait for Matt to put that up there. Now, unfortunately, Matt will have to probably. It's harder to view this pull request now that we have the active particles all merged in, but that'll hopefully go away soon. Okay, so yeah, float double and other Enzoisms that are kind of nasty. I've actually replaced in my own kind of playground all the like min max functions with slightly less common min f and max f functions, just because I was running into similar roadblocks between Enzo and other pieces of code that were not written with float double. And I don't think it's actually that bad, so I think that should be on our roadmap to clean those sorts of things up.
So I spent some time doing that in 2009 as well, and the thing that I ran into was the stuff that Dan Reynolds fixed. That was what I remember being the hardest part, was all of the Fortran, and particularly the complex stuff. And so I think Sam's probably right. It's probably doable now that the Fortran house has gotten a little bit in order. And it sounds like Sam's done it.
Well, I did like the min max, but that's not as bad as the float double because there's
Sure.
Find. Okay. The next thing up is the libconfig, or rather new config. And so it seems like, let's see, I haven't actually looked at this recently, and has anybody else thought about this recently?
Nope. I have not.
It should be moved. It should make its way in. It's just it needs to be carefully looked at before it goes in to make sure that it works with all the problem types and make sure that all the work that people have put into it that it still continues to work after it's been put down for a while. I'm not sure who wants to manage it now that Mike probably can't be counted on to manage it too much anymore. But I think it is an overall plus. It's much easier to deal with these libconfig parameter files than current Enzo parameter files.
Yeah. Something is going on in this conference room, and polycoms are going on all over the place, so I'm going to...
Well, what's left to do? Like, someone needs to go through and check that all the problem types have been done. Because I'm trying to remember, I worked with Mike on this the last development meeting, and I think we got most of them, all of them. It's just if people have introduced things since then. So that would be the only thing. If people have introduced new problem types since the last development meeting, they should maybe take a look at this and try and put their files into this format, possibly. Yeah, if they want to include it in 3.0. Is that?
I think that's right. And I think that the biggest impediment to it going in is the fact that like until it actually goes in, it's just gonna.
Yeah, we're gonna always be behind until it actually goes in. I think that's right.
Yeah, I would be in favor of, as soon as we can get it caught up, is putting it in so that it doesn't drop behind again.
So what was holding it up before was the active particles pull request. And now that that's in, there's really nothing holding up its acceptance.
Okay.
Well, I think then as long as we update it to match what's in there now, and I think that what we could do is just take a look at write parameter file and all of the diffs, or set default global data between the last time it was done and the present, and we could call it good. Oh.
What is this?
And stop messing with the chat. Yeah, I agree.
Yeah, I think it's...
So just mechanically, Mike owns the repository that opened the pull request. Should we decline it and have somebody else open the pull request, or like try to contact him?
I think we should try to contact him first because he put so much time and effort into it.
I agree. And he may also have an idea of where there may be, remaining issues or anything, really.
Yeah.
Okay.
And it's not entirely clear. So I just clicked on the edit button. Don't click the update button, but I clicked on the edit, and I was trying to see what else was new. It seems like there were some fixes, and perhaps he was keeping up with some of the changes as they were happening. So it may not be as bad off as it sounds, because there were changes up until like April of this year.
Yeah.
Okay.
So I'm gonna cancel and get back out of it, but.
Well, okay.
Does anybody? Yeah.
I mean, do you want me to? I can email Mike if you'd like, and just ask him what the status is, and then take a look at what maybe needs to be done.
Yeah.
Is that okay?
I think that'd be good.
Yeah, that'd be great.
Because I was the one after him who had my hands the most dirty on it the last meeting, at least. Okay. Yeah. All right, I can do that.
Great. That'd be fantastic. Okay. Let's see. Matt's updated the field request, or the field objects pull request. Are we? I've already approved it. If somebody else wants to chime in and possibly merge, I think we should go for it.
All right, someone want to hit the button?
That says the
Britain, hit the button.
Display.
Okay, I'm hitting the button. 3, 2, 1, button.
And so there's
Oh, wait, I have to hit it.
there's a lot of activity on Enzo 3.0 today. So if there are likely issues that will pop up, so please PR them as you run into them. Just out of curiosity, are there people that are planning on working actively on 3.0 soon-ish?
Yeah.
Well.
Okay. Good.
Hand raised.
I've been playing around with the active particle, galaxy particle stuff, so I'll be using it along with both of my current grad students.
So Greg and I implemented a momentum feedback method in the old StarMaker algorithms, and that's sort of made for active particles. We got around it by just shifting feedback zones away from grid edges as needed in the Galaxy runs we did, which wasn't great, but not too bad actually. So, but we want to put it into active particles, and Cameron was gonna spearhead that porting of that. He's not on this, but is he? No. Okay.
He never got
But we've tested this extensively in both Galaxy runs and idealized cases, and that's ready to be put in.
I think Cameron is watching, and he said he'd forward anything to me in chat, in a private chat, and I can bring it up, but he hasn't said anything yet.
Okay.
I'll let you know.
This just in from hitting the button. I can't hit it because there are conflicts in the merge, so I think some things need to be worked out.
Address it.
Okay.
Okay, cool. I think we are done with PRs, unless someone posted one in the last few minutes. So maybe we could do like a quick rundown, like a minute, talking about the broad brush overview of what's going on right now, what is currently being developed.
Should we look at that Google Doc you pasted?
Yeah, let me grab the link again. I'll paste it in the chat here. There we go. All right, so by the way, has anybody heard from John?
No.
He's in Japan.
Oh, okay, maybe he didn't. Okay.
I didn't think he went until next week.
Oh, well, he posted, maybe he's on vacation then, because he posted a photo from Alaska.
Oh, yeah.
I just assumed.
Okay.
If he was on his way to Japan and he ended up in Alaska, he should be happy to be alive.
Yeah.
Well, it is still
Well,
not
he's going
that
to Japan next week, so he is around, and he is alive.
Okay. All right, so I'm going to just start with the OpenMP. The short of it is I've spent quite a bit of time in the last month or two ferreting out a few things that were causing more than kind of acceptable levels of differences between non-OpenMP and OpenMP. And I think we had to significantly reduce the amount of threading there was, especially in, I think, like rebuild hierarchy, but it is now pretty close to ready, and Britain has been trying some out on some fairly large runs, and I've been trying some stuff out as well, so I think that'll be ready to go in about a week or two, at least to have a pull request. It will need documentation, though, as well, so.
Just out of curiosity, what was causing the differences? Were there like race conditions or something?
I believe so, yeah. Basically, I just went through and slowly pulled out each file that was causing a problem, or where there was still a problem existing until I was out of files to pull out. So it wasn't very fun, but it was effective. And I think Britain has been getting kind of 2x speed up on kind of 6 cores, which isn't too bad, especially if you need the memory for everything anyways.
So threading over 6 cores per node, and that's compared to 6 times as many MPI processes?
No.
Just on 6 cores.
N MPI processes in both cases, but then in one case you have 6 threads running on top of that as well.
Okay.
So ideally it would be a speed up of 6, but and I think there are some spaces that are still there's still room for improvement there. So, anyways, that's about it for that, I think.
Oh, Sam, do you have any plans to move this to Enzo 3.0?
Yes, especially since now that field objects will be in there, we can take advantage of a huge amount of speed up in very few numbers of lines of threading. So yes, that is the plan, is to move it there as quickly as possible.
Okay.
All right, active particles.
So we've already talked about this. I just want to bring up, I realize there's a lack of documentation. I want to put it on myself to write some documentation for active particles.
I think everybody else is happy with that outcome.
Yeah, I think so. Okay. So the split refinement thing is something that I was working on, that instead of finding the smallest rectangular prism that covers the zones that are subject to be refined at the next stage, it kind of does it by splitting a grid in half in one direction, then the next direction, then the next direction, until you get down to a size that you want. And it's working pretty well. There's some hang-ups when you have some nested simulations going on, that you can end up getting way too many grids, or it's just not quite right. But the plus side to this is that grids stay roughly the same size, and so you get, in principle, much better load balancing. So it's not that big of a change, but I just need to document it and work out a few of these kinks with the nested sims.
Cool.
Anybody have any questions on that?
So the volume that would be covered is obviously less, but like how much less?
So it's more that it's actually basically less efficient in terms of it covers more cells than you really needed to refine based on your refinement criteria, because it doesn't try to then shrink the grids in around those refined regions. So instead it just splits, and so it ended up looking more like almost like a flash simulation or an octree simulation. And it's just kind of funky, and it does some interesting things for load balancing.
Well, it fairly substantially improved the performance, right?
I wouldn't say substantially, but it did improve it. So, like, if you're running where you have a lot of zones on like the highest level of refinement, it seems to do a little bit better, especially if you also use the load balancing 4, where it kind of does the load balancing with nearest neighbors are closely connected in processor space. So it helps get that kind of a little bit more stable.
Cool.
Does it improve the surface to volume of grids as well?
Massive.
Yeah.
That's awesome.
Well, anything that makes it more like a cube ought to, right?
Yeah. Cool.
And it also makes it much easier. So Enzo will generate a basically, totally not understandable by a human hierarchy. This makes it much easier to debug and figure out what exactly is going on in your simulation. You don't have thousands of tiny grids everywhere.
Yeah. So I have some other things in there that kind of allow it to be multiples of some value as well. So maybe you want 8 cubed grids, but then it'll also be okay if it has a 16 cubed. So there's some things to work on and flesh out. But I think it's ready for a PR basically.
Will it kick out if in this process you wind up with grids that have no covering? Will it kick out unrefined zones? So I mean, if I've got some funny shaped object that has that the old version would have cut out unflagged zones, will this also kick out new grids that don't have flagged zones?
Only to some level. I think you end up with like level -1 coverage of those.
Okay.
If that makes sense. So if you needed these two, you'd also get grids here, but you'd then only get refinement into these, so then you'd split those, right?
Okay.
So yeah, it is less efficient in that.
But is that something you think would be easy to do?
Possibly.
Okay.
Yeah.
You can't have 2-level jumps.
Yeah.
Oh, do you have the ability to enforce single-level jumps with this?
I don't think so. No,
Okay.
especially not across processor boundaries.
Right. I think that's gonna be a running problem.
Yeah. Okay.
Too bad, but.
Apparently, Jeff has information from Cameron on the shear refinement.
Cameron asked me to read a prepared statement. My PR deals with modifying the shear refinement criterion. Previously, it had been created several years ago. for a specialized situation when the sound speed was assumed to be 1 and dx, dy, dz were assumed to be 1, and ppm was used. Furthermore, it said it was for refinement on shear, but actually refined on shear plus vorticity. I've corrected it to work when all of these assumptions are incorrect. Zeus also works now, it scales to the sound speed, etc. Still testing and need to document, but will be ready imminently. The change sets are in my repository. Also, please note, this may necessitate a modification to the method paper since the shear refinement formalism is modified to be simply for shear and not shear plus vorticity, unless we want to retain the shear plus vorticity and make an additional criterion just for shear. I'm a little unclear on... oh, never mind. Yes. I was going to say something monumentally stupid. That was not Cameron's. That was just...
Okay.
Cool.
Duly noted, I guess.
Where is the method paper? Speaking of the method paper.
Greg?
Do we want to talk about that now or at the end?
Oh, we
It's
can
on the internet.
Why don't we talk about it at the
talk
end?
about it later. That's fine.
Okay. All right, Christine, AMR restriction based on less refined particles.
Okay, so I mean, this is in my branch, and I've used it, and it's actually a pretty simple fix. It was just that there were some changes that went along with the nested cosmology initializer that, for my particular use, were needed, and that was making merging difficult because there was apparently a bug in Enzo Dev in the nested cosmology initializer. So I was working on this today. I did a merge. It compiles. I've done just the simple nested cosmology tests in the run directory. They work, and now I'm gonna sit down and make a simple test for the must refine particles. I actually never really did that. I just sort of ran smaller scale versions of my science runs. So I have a merge. I'm testing it, and I need to sit down and also write some docs about its use in cosmology runs. It's sometimes confusing to explain to people how this can be really helpful. And I should also say that I've been communicating a lot with Jihoon because this framework is actually sort of needed for the Agora project to make our refinement restriction, like they had some word for it, like masking region, to make that consistent with some of the other codes. This is actually the way we would do it. So I've been communicating with him, and there's going to be some changes in music that will make this even easier in Enzo. So music will now output a particle type, which will be, a flag to tell you whether the dark matter particle is must refine or not. And so that will just be bundled with the initial conditions, because part of what was tricky currently is that particle IDs are assigned in the initializer, and it used to depend on the number of processors, so you could get different IDs depending on how you initialized it, and so you couldn't just give a list to Enzo. That was actually kind of challenging. So we did some very not bad changes, but complicated changes to make that work. But if they're just going to come with the initial conditions, that will be a lot easier and cleaner. Okay. So I guess it's still a little bit of a work in progress, but I've done more on this this week than I have in a while. So I'm optimistic for getting it into Enzo Dev. I don't know. Are there any comments?
So I'm just curious, what's the difference? What's new in this in what you're working on?
Well, so basically, I mean, so there are must refine particles in Enzo, and you set that flagging criterion, and it will flag the cell with the particle. The issue is if you want to restrict AMR based on any other criterion to just cells with that particle. That's what's different.
Okay. That makes sense. Thank you.
So basically, it's a way of doing a Lagrangian region that is, you know, not rectilinear and will move with the collisionless component that you're simulating.
Cool.
Okay.
Do you want to?
Yeah, I can just keep going. Yeah, so I mean, in my branch, I just have a bunch of things that I've never merged in and might be useful to people. So this was just a very simple calculation of just average shielding cross sections for, you know, H1, HE2, HE1, where you just give it the slope of the ionizing field, and it will just calculate a cross section for those ions based on that. And you know, it's pretty simple. It's something I used in my paper, so if people wanted to use it, they could use it. And then the next thing is the momentum feedback. So Greg and I did a lot of work on this, and so we have something that works and that we've tested in 2 ways. One, we've just set off you know, individual star particles in just, you know, a uniform box of gas, and, you know, just check to see how it changes with resolution, with cooling, without cooling, and the different fractions of momentum that you inject. So basically, the way it works is it's almost exactly like the old Chenin-Ostraker method. You set a fraction of the star particle's rest mass energy you want to return to the gas, but then you, on top of that, set a fraction of that energy you want to be returned in kinetic form. So if you set it to be 0, it would be just all thermal, like the Chenin-Ostraker method, except it would be distributed over a couple of cells, which there was already a distributed version of that anyway. So with this change, you could then set that fraction to be, say, 30%. So then it would inject 70% of that energy into the thermal energy of the gas, and then it would calculate for the remaining 30% of the energy how much you need to change the gas velocities of the surrounding cells, given the amount of mass you're also injecting into the cells. I should mention that as well. And how much you need to change that velocity, and it does that change self-consistently for that fraction you've set. And so that's implemented. We've done these extensive idealized tests, and then I have also done some galaxy tests, and actually the version of the code for that is not, I don't think I've pushed that anywhere, but basically what we did is we ran one of my old dwarf runs, and we just shifted the feedback zones away from grid edges as needed. It was only about 10% of the particles needed that done, and we just ran it like that, and there was, you know, quite a bit of difference actually for the resolution we were testing. So it's implemented, it works, and what needs to happen now is it needs to be ported to the active particles. So Cameron was going to work on that, and he's not here, but we communicated over email last week, and I told him, you know, what I'd done, and so I don't know if he's spending any time looking at the active particle stuff. I mean, I can also look at the active particle stuff and see what needs to be done, but that's sort of where I'm at with it. And there's no documentation written. We have a method paper we're working on right now, so once that's out, we'll write some docs to go with it.
Okay.
So.
Do you want to
just
anyway, sorry, that was more than a minute.
Go ahead, Jeff.
I have Cameron here. He's formulating a response to He says he's ready to work on this.
Okay.
So I guess, Christine, maybe you and he could discuss this
yeah, we can deal with it.
offline.
Yep.
Although I wanted to also, Cameron made a point earlier, just to go back to the must-refine particles. Is there any desire to have a passive fluid to do this? So like a must-refine fluid rather than particles.
That would be interesting. Yeah.
He points out that Ramses does this. I'm just thinking about it myself. It seems like that would be quite fairly straightforward to implement.
You would have some kind of color field, basically.
Yeah, exactly, right.
Mm-hmm.
And then that color field, wherever it is, you refine. I would imagine that's actually easier than the must-refine particles.
Except
but
for
interested.
Agora, it's for n-body simulations where you need the must-refine particles.
Devin, didn't you do something like this?
Yeah, that's actually really straightforward. I did it with a dust field to track to refine on just material that was originally in a crushed cloud.
So, yeah.
I guess I mean, sure. I don't know. I guess I would have to test it out in some of these cosmology simulations. I mean, for me, I was doing these simulations, zoom-in simulations of these very low-mass dwarfs that move quite a large distance, co-moving distance in the simulation volume. And I guess I would just wonder how much that field would diffuse over that, large a distance. But things like clouds, that would make sense. So, I mean, I don't know. But yeah, is that in the code, Devin? Is that
yeah,
somewhere?
It seems like, Devin, if you could maybe contribute this, it could be useful.
Yeah, it's in my personal code base, but I could actually probably clean it up a bit and put it in.
Britton, maybe you want to talk about the items you have there?
Yeah, sure. So both these things, they weren't hacks, but they were adjustments that needed to be made to get Enzo to play nicely with running with conduction in a cosmodule simulation. So the first issue is, well, they both basically come down to the fact that the explicit conduction solver we have introduces really, really short time steps, and that exposes a lot of interesting things in the code. So the first problem, of course, is related to well, a little bit to memory fragmentation, but also just to having short time steps and having to rebuild the hierarchy like a million times, or not a million, but thousands of times, whereas maybe a factor of 100 more than you would have, or more. And it occurred to me that in general, when your time step is limited by conduction, the conduction solver is not actually doing much to change the density field, and so it's not really doing much to change what the hierarchy should look like. And so,
it's doing precisely nothing to change the density field, right?
Well, yeah, it's doing right, except for changing the temperature field, which will yield changes to the density field eventually. But yeah, it's explicitly not changing the density field at all. But so the point was, well, then we don't need to be rebuilding the hierarchy on the conduction time step. And so essentially what this involves is calculating a global time step with conduction, or just from conduction and from everything else. And if the conduction time step is shorter, you always run on the shortest thing like normal, but you only rebuild the hierarchy based on the time step of everything else. So you march forward a set amount of time, and then you rebuild the hierarchy, and then you check again how long you need to go before you rebuild it on every level. And right now, I mean, in theory, if there were any other sort of thing that would have a really short time step in which you wouldn't actually be needing to rebuild the hierarchy, you could always lump that in with the conduction time step calculator and calculate those things separately, move the code forward on those timescales, and then rebuild a hierarchy on the other timescale. So that's what that is. It made those runs go a lot faster. But again, it's kind of a niche thing, because if you're never going to use conduction, then you probably won't use this. But if you are, in the setting in which I did, it's probably absolutely necessary.
I can dream up other situations where that might be useful. I mean,
all right.
Yeah.
I actually have coded ohmic resistivity, which I'm guessing is what David was thinking.
Yeah, that's one of the things I was thinking. Yeah.
Would I be able to use this as
Absolutely.
is? Good. Okay. Because
yeah.
I haven't pushed that yet.
Okay. Yeah. It's just in the time step calculation part. It just it breaks it into two things. I mean, if you're interested in this, we could talk about it separately. I could show you exactly what to do. But
yeah.
I think I might have even documented it in my branch in advance of having it a part of the code base. But it's basically just it's just one. It's actually two flags. It's one flag to turn it on, and one to say what is the minimum level at which you do this. Like, if you don't want to do this on the first or second level, you can reserve it for only the most refined levels where it's a real big problem. But that's all there is to it. And so if anyone has any objections to it being added, or any suggestions for how it might be better, I'd be happy to hear them.
Britton, so it's possible for the hierarchy to get into an inconsistent state where you're actually breaking one of the refinement criteria, and then that gets corrected the next course time step when you actually do rebuild the hierarchy. So have you explored whether that's actually an issue, or have you thought about that at all?
What do you mean by an inconsistent state?
So let's say I've got some collapse happening in my simulation, and you're taking a bunch of these short time steps, mass is accumulating in some cell, that cell gets, the density gets high enough that you would normally trigger refinement in that cell.
Sure.
But because you're taking short time steps, you won't actually trigger that refinement until the next course time step finishes.
Well, so the argument.
Is that an issue?
Well, in theory, this isn't how this is inherently supposed to work. Is that this shouldn't be an issue? Is that if, for example, with conduction, if conduction weren't there, you would integrate on this longer time step anyway, and so you're still rebuilding the hierarchy with the exact same frequency as you would before. And so, in theory, it shouldn't really change anything, unless you have, this crazy nonlinear thing where you make tiny changes in this short time step thing that all of a sudden throw your system in a completely divergent path. But that really shouldn't happen. So, no, I mean, this is exactly what this is supposed to be. Is that we shouldn't be changing the things that change the hierarchy on those timescales, and that's why you would allow it.
Or at least by a lot. You might get
or at least by a lot.
Inconsistent state, but you won't get into a radically inconsistent state.
That's correct.
Okay. So maybe just, if you get a chance, take it and PR it, and we can take a look.
Okay. All right. That's great. I will do that. Okay. And then the second thing is yet another thing that I had to do to make conduction work in cosmodule simulations. And this has to do with the same issue, in fact, that the time steps are super short, and we were using this Chen and Ostreicher star formation routine in which the mass of the supposed star particle that would be created has in it in the numerator the time step, the local time step. And so if it's super short, you want to create a very low mass star particle all the time. And unless you have the minimum mass really, really low, which results in getting a ton of really low mass star particles, what you get instead is you get gas building up at the cooling floor, waiting to have a dynamical time, since the dynamical time is in the denominator, short enough to drive up the mass of the potential star particle. And of course, when you have conduction on, and you have cold gas just persisting, surrounded by hot gas, you end up creating a really nice heat sink, and it destroys everything. So let me just put this a really short way. If you ever want to do a conduction simulation with star formation, you need to get rid of having this local time step in the numerator. And so that's exactly what I did here, is I basically said, instead of using the local dynamical time, you just set a dynamical time. You set a star formation time step, or you set a time interval over which the Chen-Oestriker linear rise and exponential fall off will happen. And so you can set it to be a constant that sounds physically reasonable, like a few million years, 10 million years or something.
And that's actually analogous to how some other star formation algorithms work.
Yeah, it absolutely is.
That the original Chen-Oestriker star formation algorithm only makes sense if the time step has something to do with the dynamical time, which you're not.
That's right. That's exactly right.
Yeah, actually, not to be completely pedantic, but it really only works as long as the time step is pretty long, right? I mean, in the Chen and Oestriker simulations, the time step actually is just is Courant limited. It has nothing to do with the dynamical time. So it only, so basically all you're doing is just all you're doing is just using that time step to take away some gas, but not all gas. So anyway, it's not important. So.
Right. Anyway, so that's all this is. Yet another flag, yet another parameter to choose this over the old way and to set a constant value. I'm not philosophically in favor of every linear combination of ways to make a star, sitting on top of each other. But that being said, if you ever want to use this in the context that I just described, you need to do something like this. So, I don't know. Is it something that should be in there, or should I just leave it in the fork and tell people?
I think it would potentially be useful, especially just for any case if you have too deep of a hierarchy or something. You may not want to form it on that time scale, and you may want to make slightly larger stars so you don't have a trillion particles, right?
That's right. Right. Okay. Well, should I just issue a PR and let people take a look at it then?
Yeah.
All right. Okay. That's it then. So I'm going to pass the mic to Oishi, O'Shea, and Hallman to talk about viscosity and subgrid turbulence.
I think I've been volunteered to deal with this. So, okay, so viscosity and subgrid turbulence, this is something that's in the works. For a variety of reasons, both Jeff and I need viscosity working. So isotropic and anisotropic viscosity, one of which needs the MHD, of course. It's actually really simple. It goes in just like the conduction. It uses essentially the same machinery. At this point, Eric Hallman and I are working on it, and it's all a matter of how quickly we get our acts together. And the answer is not very quickly. The subgrid turbulence is also for the same project that Eric and I are working on, where all we're doing is we're implementing a subgrid turbulence model from Scannapieco and Bruggen. And again, it's all really simple stuff. The viscosity certainly would be useful for other people. I don't know if the subgrid turbulence is going to be broadly useful.
I think.
Oh, go on, Jeff. Sorry.
Sorry. What I was going to say is I think it could be made to be quite generic if we write it in such a way that the model can be sort of like imagine it's a function pointer, right? So like the thing that does the construction of the subgrid model, if we could make that so that you could do energy dissipation at the grid scale by any number of these things, which takes incoming variables, then I think it could be quite useful generically in a lot of cases.
Okay.
Does that make sense?
It does, yeah.
I mean, yeah, because there are a number of things that I would find very useful if I could have a particular MHD subgrid model or something, right? And I think if you're thinking about making it at all, I think it's worth the effort to make it swappable.
Okay.
That would be rad.
And it should be pretty easy. I mean, so the way that they're, because essentially the way that it works is, I mean, it's a diffusive term, right? So all it's doing is looking at what's locally going on, and then taking away kinetic energy and turning it into thermal energy. And that's something that, you know, there's a lot of infrastructure, and then about 4 lines of code that determines E dot essentially. So that should be pretty straightforward. Yeah, I think you're right. So with very little effort, we can make it so that essentially in the middle of that, it just calls a function. Yeah, that should be cool. No problem.
Right. Exactly.
Okay. Yeah. Thank you. But the approximate time frame for this is, I mean, it's funded by a Chandra Theory grant that we have another 4 months on. So probably it'll be done before then. But it also doesn't affect any infrastructure outside of those routines. So, you know, so it should go into whatever release, you know, it's done by. So that's kind of the plan. Make sense?
Sounds great.
Okay. So next up, Greg.
Right. So with Jean-Claude Passy, who's we've been working on this adaptive particle mesh solver, which actually was the original gravity solver in Enzo. And the idea is very simply it breaks up the force law into a set of different scales, contributions from different scales, and then sums those together. And it's nice because it's completely FFT based, and so it gets around this issue of boundary conditions with the potential solver. It's still under development. It's working as long as particles don't move. If particles move, then still some force inaccuracies, but we're getting there. I don't know, speed-wise, I don't know. It won't be super fast, but it's looking like it won't be super slow either. JC is doing most of the development, and I don't know what the timeline is. Maybe, who knows? It's debugging code. Maybe, hopefully a few months.
I would just comment, Greg, that something that comes up every once in a while is adding a p-cubed-m, you know, adding a particle-particle term inside of Enzo. And having that would make it really easy to do, you know, having the adaptive particle mesh would make it really easy to do that, right? Fourier transform based. That would be fantastic.
Yeah.
Cool.
Okay.
Okay. Let's see. Devin put himself down for the must-refine fluid, so I think it sounds like he's going to try to implement a fluid color field that you can refine on, and it works for his dust destruction simulations really well. So that's great. And so that's just a follow-on to the must-refine particles that Christine was talking about.
Yeah, this is John. There's also a must-refine by Metallicity. So, I mean, if he hasn't started on that yet, He can look at what I've done.
I believe he's already implemented it.
Sorry?
He's already implemented it.
Okay, so must be another refined criterion.
Yeah.
Is there any reason why we ought to ask him to try to combine this with refinement by metallicity, or make metallicity a special case of the must-refine fluid?
That could be a case, yeah.
Yeah.
I mean,
yeah, I think it'd be better to get rid of the must refine by metallicity and just make it a must refine by fluid field.
Yes.
Like by color field or by tracer field. And then you specify what field and you're good to go. Or even multiple fields, right? So
exactly.
So I think Devin says yep.
It seems that this would be really easy to do in Enzo 3 with field objects if you could specify like a field string and say, I want to refine by this. And instead of having to hard code in which field every time.
Yeah.
So
that would be rad.
Field objects.
Yeah.
Okay.
All right. Dan.
Yep. You guys hear me?
Yep.
Okay.
A little quiet, but we can.
All right. Let me. Hopefully, maybe this will work. Okay. So I wanted to update. I've been continuing the work on the AMR FLD and AMR gravity solvers, and I haven't gotten significantly further than I was our last development meeting because I've been working on some other stuff. But both of them seem to work. They give the right answers for a small number of verification problems. I want to do more verification problems and optimize how they're set up. Specifically, I'm putting in isolating boundary conditions. Those aren't going to be useful for cosmology, but they'll be useful for verifications. The only thing I don't really like is specifically for the gravity one, how I have to handle the ghost zone updates for these larger potential fields between levels as I go through the solve. And so I think it's fine. I just think it's slow, and I wanted to potentially look into this field object stuff because I think that might make it fantastic. But we'll have to see. And then, or of course, if this APM solver seems to work quite well for AMR gravity stuff, then I have no need to have 17 solvers for the same thing. So with that said, I'm kind of in the middle of a few things. I don't really see a need for help right now, because I guess that was one of the things we were supposed to talk about in the email. But that said, I'll try to make some good progress soon.
Cool.
I just want to say, actually, Dan, it's the solver would be quite different between the APM solver and this. So don't drop it.
All right, that's fine. Yeah. Okay.
I think it's a really exciting development.
Okay. I think we've made it through all the items there, unless Britton is about to write something else new down there.
Oh yeah, I just want to say something really quickly, if that's okay. It's not totally Enzo, but I just want to make people aware of it. So for the Agora project, which I'm sure everyone has heard of, is this big galaxy formation simulation comparison. I was charged with a couple other people of trying to help out making a common cooling package so that we could all be doing the same radiated cooling. And so Mike Coolin and Matt and I worked on basically extracting Enzo's cooling solver into a library, and then we just sort of cleaned it up a little bit, and I added some more recent radiation. Well, actually, Mike added some more recent UV backgrounds, and instead of doing them with these piecewise polynomial functions, we did it just with like reading from a table in a file. So you could, from now on, you wouldn't have to like spend half a day trying to fit, the values to some sort of redshift dependent thing. You could just get the data from whatever publication and make a file. Anyway, so right now it's called the Grackle. for I don't know why, because I like that word and I like that word. But anyway, it's just basically Enzo's stuff, but taken out, cleaned up a little bit, and put into a library. I think in theory, it could continue to be polished up and improved, and it actually has been. I've made it work by like relinking it to Enzo, and I think Nathan is actually using it.
Mm-hmm.
So, in theory, if we wanted this to be a modular thing that could actually be used for other people and stuff, this would be a way to go if people are interested in it. The other nice part about it is Nat made some really nice Python wrappers for it, and so you can call it from Python, and this actually has the benefit of you can do really nice things like iterate the solver until it converges without having it change the temperatures, and you can make really nice cooling rate plots. So I'm gonna throw a secret out there. The cooling rate plots that I made for the Enzo method paper came from that. So it's a scandal. But so anyway, the website for it is it's just a Bitbucket repository, and I actually had been meaning to send out an email just explaining to everyone what it was, and if they wanted to play with it, they should feel free to. So maybe I'll just reserve sending anything else and just go ahead with that plan to send out an email, and if anyone is interested in playing with it or using it or even contributing to it, they should definitely feel free. And there's some docs right now on how to add it back to your code. I mean, it was mainly, as I said, designed just to lend to this Agora project, but I think it could have a future on its own too. That's all.
That's awesome. Probably makes testing a lot easier too.
Yeah, I mean, it's totally, you can test everything in isolation without having to run a simulation, which is quite nice.
That's great. Okay, well, I think we're at kind of our nominal 90 minutes, unless somebody, John, you came in a little late. Did you have anything else you wanted to mention?
No, I went through the spreadsheet, and I guess you guys talked about the hybrid version, and you gave an update and active particles. Yep. And what was the for active particles? I mean, there's that big PR. I mean,
it merged.
It's no longer a big PR. It's now in Enzo 3.0, and we can issue pull requests against the Enzo Dev branch in Enzo 3.0.
Okay.
So that's all in there. Yeah, John, if you wanna work on active particles in the future or you discover issues, please let us know.
Yeah, so I have a student. He's working on active. I got him to work on active particles. So,
oh, awesome.
Yep. So he's working off your branch, or I think he forked your branch because that's where all the changes were. Because I didn't want him to wait for the PR to be accepted.
Yep. Now it's in there. And also, if anybody has any issues with active particles, please feel free to talk to me. I probably have the most up to date.
Yeah, or even just like fill out issues on the Bitbucket tracker.
Yep.
So.
Okay, and the last, any other comments on that? Okay, then the last thing I wanted to say was that actually I sent an email Friday about this.
For a second.
There, I just muted Dan.
Okay.
Matt and I have been chatting about this for a while, and we'd like to host an Enzo Developers Workshop in spring of next year. Brian, I think you also volunteered, but it sounded like you were happy to move it to the one after that.
Yeah, whatever works. I mean, honestly, I volunteered it in the absence of anybody else, so that's fine. It's all yours. I'd rather go to Manhattan anyway. So East Lansing in early spring is wretched.
Well, get exact dates. If you have suggestions for dates, feel free to send them to me. But we'll be canvassing people shortly.
approximately when are you thinking? Like
Well-
March, April, or?
Yeah, it probably is, because, yeah, probably in that time frame. So not really early, because partially because of weather, and I think we need enough time to put this together. So.
Sure. Well, the APS meeting is right at the beginning of April, but other than that, I can't do everything. But if you send around an email, then maybe people can just respond back with weeks that they,
No, I think we'll do that.
Okay.
And there, on the same subject, I was thinking about having a mini dev workshop in the summer, next summer, because XSEDE's going to be in Atlanta, and I know a few people go to XSEDE. And piggyback on top of that.
Definitely.
And whoever's in town.
Yeah,
We can
I'll
all
probably
meet up after that. So that's in July.
Awesome.
Which is a good time to be in Atlanta, I believe.
Oh yeah, you can sweat your.
Yeah.
All right. Yeah, but that's maybe like 5 people, whoever's in town. That's what I was thinking.
Sounds good.
Okay.
Do you guys want to do another one of these in maybe 2 or 3 months, or maybe earlier?
Yes.
If you're interested. Yeah.
Yeah.
Maybe like in between Thanksgiving and winter break, something like that.
Sure.
Sure.
Finals.
All right, I'll put it on my calendar to send out a request for dates in about a month, and then we can figure out when that'll work.
All right.
Is that okay?
Sounds great.
Sounds great. Thanks, Sam.
Sure.
Thanks.
All right.
Take it easy, guys.
Everyone.
Bye.
Take
Bye.
it easy.
See you guys.
Bye.